Greetings, class. This is a tutorial on the number manipulation you are going to have to do in lab this week. You're going to have to copy numbers from an Excel spreadsheet, get them into MATLAB, and plot them there. Well, let me show you the easiest way to do that. I have a couple of columns here in an Excel spreadsheet, and I want to get them into MATLAB, which is right back here. So what do we do to do that? Well, hang on a second. All right, so now I've got my MATLAB information, or excuse me, my Excel spreadsheet here. To get it in the MATLAB, I just highlight the column of data that I'm interested in, and I copy that. And then I go into MATLAB. Notice that I want to put in the time data. So what does it look like? I'm just going to copy what I just cut out, and it shows up as just a series of numbers. If I want to make that a column vector, I can just put a column vector t, time equals, and then I have the open square bracket here and my close square bracket down here at the end, and there it is. So now all of a sudden t is a column vector. If I want to get the position data in there, I'm going to call it x. I know that I need that opening square bracket. Let's find my data. MATLAB wants to cover it up. Here we go. I'll just shove it out of the way. There's my position data. Let's copy this. Let's copy that, and then let's come back in here. Let's paste it right there. All right, and then once again, I have another column data, and I can put a closing square brackets at the end of that. All right, so at this point, I have two column vectors. I have a vector t, which is this set of numbers, and position x, which is this set of numbers. If I want to plot those and see what it looks like, I'm just going to use the plot command. In the plot command, the first variable is your horizontal, so in this case it's time. The second variable is the vertical one. In this case it's position. All right, let's save this, and let's run this and see what we get. All right, so there's my plot. Of course, now I'll need to put in X labels and Y labels, and I'll need to put a title bar up here. But you guys can figure all that out. What shows up in my command window down here, my time vector, my position vector, and then the plot. So that was fairly straightforward. For our second activity, this week, we're going to figure out how to symbolically solve equations using MATLAB, which is very powerful, and this would be very useful for solving many difficult problems. I just didn't make up a problem. What I did was I pulled example 8-2, which is on page 23 of the rattan text. Excuse me, page 231 in the rattan text. There's that example. All right, so this is a third order equation, and I'm going to solve this symbolically. First, I put in the constants, and these are from the problem. Now, the symbolic thing in here is t. I'm telling it to treat t not as a number, but as a symbol. So when I say it's a times t squared plus b times, a times t cubed plus b times t squared plus c times t plus d, there's my third order equation. The numerical coefficients are whatever I assign them up here. And if I want to plot that, use the easy plot command, which is found in chapter 11. So go read chapter 11. You can find what's going on with easy plot. I'm going to have it plot that function from 0 up to 10. Let's see what this is going to do for us. If I save that guy and then run it, So, there we go. There we go. I just had to go think about it for a while. All right, there's our plot. There's our third order equation. And from looking at this, we're going to take the derivative in a second, and it looks like the derivative is going to be 0 at around 3 and should be 0 at around 7. All right, so let's get rid of that. So now this equation is also being treated as a symbol because it has t in there, which is a symbol. All right, and we can plot it. Now I want to take the derivative of that equation. I can do it numerically. I don't have to calculate it out. And what I can do is this simple little command right here. I say diffy, and it'll take this equation and find the derivative of that with respect to t, because t is my symbol. It'll differentiate that, and then I want to plot it. So I'm going to create a new figure for it to go into. I'm going to do easy plot again, only now I'm going to plot v, my velocity, not y, the position. And whoops. And we're going to put a grid in there to make it beautiful to look at. Oh boy, what terrible misspellings. There we go. All right, so we're taking the derivative of y, our position y, and we're going to plot it. And it's very easy to do. Let's save that, and let's run this guy. All right, so we'll look at the figures here in a second, but first I want you to notice what showed up in my window down here. There was A, B, C, and D. So y was 1/3 t cubed minus 5t squared plus 21t plus 10. And then v was the derivative of that. So when we take v, we get t squared minus 10t plus 21. So it took the derivative of y, of our position, to get our velocity. There's our position graph again. And when we plot the velocity graph looks like this. So there we go. We expected our derivative to be 0 at 3 and 7, and are they? We go over here to 3 and it's 0. We go to 7 and it's 0. So yes, that's what we need to do. So that's how you put in a symbolic equation and how you symbolically find the derivative of that, which is very powerful. We'll be using this a lot, so play around with it. Have some fun.